It's my pleasure today to welcome Giancarlo to the next installment of the Research Champion Talks for cyp-c. And Giancarlo is a research associate here at Pogo. So he works on a number of projects with me and some other team members. And he's going to present today on competing risk analysis. So Giancarlo.
Great, thank you. So the title of my talk is an overview of competing risk analysis and time to event outcomes using SAS. And I want to thank Jason for allowing me to give this presentation. So first I'm going to start off with a little bit of an outline of what I'm going to be discussing today. So I'm going to give a quick refresher and overview of what exactly time to event analysis is. I'm going to explain what is a competing risk and why do we need to consider them. Then I'm going to discuss some of the assumptions that we need to make when doing competing risk analysis. And then I'm going to give an overview of the data structure and how we set up our data and transform our data when we do perform competing risk analysis in SAS. Next, I'm going to talk about the cumulative incidence function, and that's how we, in competing risk analysis, that's how we determine the incidence of our event of interest. And then I'm going to propose two different methods. One, the subdistributional hazard, which is a fine and gray method, and also the cost-specific hazard, which is an alternative method to quantify the risk in competing risk analysis. So a quick overview of what time-to-event analysis is. We also like to call it survival analysis, so they're the same thing. And what it does is it models the occurrence and the timing of an event outcome of interest. So we specify our origin of the observation window, which is our time zero, and that varies by our research objective and our research question, and when we choose to start following individuals. Next, there's censoring of individuals, and then when we censor them, we are no longer observing them, so there's left censoring, right censoring, and interval censoring. Dr. Jason Pohl has previously gone over this in a previous cyp-c webinar, so I won't go into too much detail, but typically we're used to right censoring, where we follow an individual up until the event of interest, we censor them, and then we're not interested of what happens afterwards. Now, the reason for censoring may vary between individuals, and that's really what's critical for competing risk analysis. And it depends also on our research objectives and our research question. So some examples of reasons for censoring that we might look at is loss to follow-up, the experience or outcome of interest, the study window ends, or they may die. So here's a brief graphic of what time-to-event analysis or survival analysis looks like. And we've seen this before. So subject A, from time zero, they're followed for 2 years, and then they're censored. And the censor, I'm using the X. Next, we have another patient, patient B. They're followed for 3¼ years, and they experience our outcome of interest. Patient C is only has follow-up time for ½ a year, and then they're censored. Same with patient D and patient E, with B and E experiencing our event of interest at different time points with different follow-up times. Now I'm going to dive into what exactly is a competing risk. Well, competing risks are said to be present when a patient is at risk of more than one mutually exclusive event, and the occurrence of one event will prevent any other from happening. An individual can experience a failure event from one of several possible causes, and with one failure cause precluding the others. So some examples of what a competing risk analysis is all-cause mortality. So death can be a competing risk for anything really, because once you're dead, you're not at risk of any other outcome. Or in bone marrow transplant studies, you can have treatment-related mortality, progressive disease, and relapse as your competing risks for the success of the BMT. So when are there competing risks, and why do we need to consider them? Well, in traditional survival analysis, it tends to focus on failure time data that have one single event type of interest, or one type of failure. Competing risks should really be considered when the occurrence of one event hinders the occurrence of other events from ever happening. So like I previously mentioned, death. Competing risk analysis also enables us to model separate survival probabilities for the events of interest in the presence of other competing risks. And that's what really gives value into competing risk analysis. So again, to my little infographic, A and B are the same. However, now we find out that patient D had a different event at half a year. And what that event was is that they actually died. So in competing risk analysis, we don't know what happens if they would have been followed up had they not died. Would they have experienced our outcome of interest, or would they have been censored? And it doesn't necessarily always have to be death. There could be other reasons as well for the censoring, which would preclude our outcome of interest and hinder the occurrence of it. So next I want to dive into some of the assumptions that we have to make when performing survival analysis. So it all applies the same to competing risks. We have to assume that the reasons for censoring are independent and reasonable. Now, there's actually no way of testing this independence assumption in competing risk analysis. And this is what's really important, is that censoring is assumed to be random and non-informative. So your competing event can't be informative of your outcome of interest. Individuals have the same future risk of the event of interest as individuals who have not been censored and have not had the event of interest. So next I want to present a hypothetical study that I'll be using to display competing risks that we might experience when doing our own research. And I'm going to use this example throughout the remainder of my presentation. So in this mock study, I'm interested in studying the effect of the treatment received for the primary cancer has on the development of a secondary malignancy. My exposure variable is going to be the intensity of treatment rating scale, or the IT3. And what this measurement is, it's really a composite measure of the treatment received for pediatric cancers. So it takes into account whether or not they had a bone marrow transplant, radiation, whether they relapsed, and it varies for the different types of cancers. So this rating scale is on a scale of 1 to 4, with 1 being the least amount of intensive treatment received, and 4 being the most intensive. And in the most intensive, we can expect BMTs and radiation and high-dose chemo. Then I want to follow my patients from their initial diagnosis, which is my time 0, and I'm going to follow them until the development of a secondary malignancy, or when I'm specifying the study ends. And for this example, I'm going to use December 31st, 2016. However, I also have to consider death as my competing risk, because if a patient dies from their primary cancer, they're not at risk anymore of a secondary malignancy. So first, we need to structure our data, and we need to manipulate our data to allow us to perform competing risk analysis. So first, I'm going to define my cohort. So I'm taking all diagnoses, or the primary diagnoses made between 1985 and 2012. Next, I'm also going to subset my cohort to individuals between the ages of 0 and 14 years old. Then I'm also going to choose patients with an ITR between 1 and 4. Now, something to note here is that if a patient had died before receiving any sort of treatment, they would not be captured in my cohort because they didn't receive anything. So they died before any treatment is received. This next section of the code is actually really important when we perform competing risk analysis or when we do any sort of analyses on prospective data. So I want to make sure that my events of interest happen within my own observation window. So in this example here, I'm choosing if the death date is greater than missing and it's before my study end window, which is the 31st of December 2016, then what I'm telling SAS, what I want you to do is set death equal to 1, and then I'm going to close that do loop. And then on the next line, I'm going to start an else do loop. So if it doesn't meet the conditions on the first line of code, then I want you to set death equal to 0. I want you to set the death date equal to missing, and I'm going to close that do loop. And what that pretty much does is, let's just say a patient in our cohort, or when we receive our data, their death date might be February 2nd, 2017. What this line of code does is that it takes that death date, it sees that it's not within the parameters that I've specified, and it sets death equal to 0 and the death date equal to missing, because I'm not interested in what happens after the 31st of December 2016. Otherwise, we might be miscounting or misclassifying our deaths. And I'm going to do the exact same thing to SMNs, because I'm not interested in anything that happens after the 31st of December 2016. And just to reiterate, this ensures that no outcomes of interest happen outside of my observation window. Next, I'm going to calculate some time variables. So the first time variable I'm going to calculate is the number of days between their primary diagnosis, which is time 0, and their death. So if death is equal to 1, then I'm telling SAS this is what I want you to do. I want you to create a new variable called time death, and this is the date. This is the difference in days between the death date and their initial diagnosis. Then I'm specifying, but if this value is less than 0, so if it's negative, I want you to set it equal to 0. And what this does is it takes care of my postmortem deaths, and it sets it equal to 0. Next, I'm going to calculate the same thing, but for time to SMN. So this is just the difference in days between their primary diagnosis and their second diagnosis. And if a patient didn't experience an SMN, then this value will be missing. Next, this is where the competing risk and data cleaning really comes into play. So I want to create a sensor date variable. And what this is, it's the minimum date between there's an SMN date, or the second diagnosis date, a death date, or the end of my observation window. So what SAS does is it takes these three variables, or these three specifications, and it looks for the minimum value between the three. So for example, if their second diagnosis date was before their death date, the sensor date would be equal to the DX2 date. If a patient didn't die, or they didn't have an SMN, so the values of DX date 2 and death date would be missing, and sensor date would be equal to the 31st of December 2016. And all this does is it creates a date variable for me that I can then use to calculate follow-up time. Next, I'm going to define my sensor variable. And I'm going to define my sensor variable due to different reasons for exits out of my study. So a value of 1 is my main outcome of interest, and this is my SMN diagnosis. Next, I'm going to specify a value of 2 as all-cause mortality, because that's my competing risk. Next, I'm going to specify a value of 0, and that's my censored variable, or my censored value. So they didn't experience any of the outcome of interest or the competing risk. So I'm telling SAS, if they did experience an SMN, so SMN is equal to 1, and the diagnosis date, or the second diagnosis date, is before the death date, or the death date is missing, then I want you to create a variable called sense_CMP risk, which is my competing risk sensor variable, and set it equal to 1, because these are my outcomes of interest, and these are my SMNs. Otherwise, if death is equal to 1, but the patient didn't have an SMN, then I want you to set this value equal to 2, and these are my competing risk patients, or competing risk cohort who died but didn't experience an SMN. Otherwise, set it equal to 0, and these are my patients who didn't have an SMN or die, so they're pretty much, they end the follow-up at the 31st of December 2016. And then finally, I just want to calculate follow-up time. So my follow-up time is using the sensor date, which I created at the top of this program, or this code, and I want you to and it's the difference in dates, or in days, sorry, between the sensor date and the first diagnosis date. And really what this section of code is it defines my competing risk and my follow-up time. And then at the bottom of this code here, I'm creating a new variable, which I'll show later on in the presentation. But what this variable is just a dichotomization of my sensor variable, which I've defined previously. So if the competing risk value is equal to 1, which are my SMNs, create a status variable equal to 1, so I know those are the individuals who had an SMN. Otherwise, set the status equal to 0 because they didn't experience an SMN. Once I run this code, I look at the log, and I can see that I have 9,659 patients in my cohort. And I like to add that little note there so I can follow the ends. And I know when I do data cleaning steps, I'm not missing any individuals. So once I run that code, I want to see what my data looks like. So first I want to focus on subject 26. So subject 26 both died and had an SMN. They also had the most intensive treatment received. From the code previously, the time to death, which is the time between their death date and their primary diagnosis date, is 2,453 days. However, the time between their first diagnosis date and their second diagnosis date is 2,094 days. Since they experienced an SMN, their sensor value is equal to 1 because that's my outcome of interest. Now I want to show what the minimum statement does. So we can see in sensor time, which is the second to last column, it's equal to 2,094. And that's because it's the smaller date between the time to SMN and the time to death, which is what we want. So even though they died after their SMN, their censored or their follow-up time is the time from their initial diagnosis up until their SMN. And the status value is equal to 1 as well. Next, I want to highlight subject 3. Subject 3 died, but they didn't experience an SMN. So their time from their initial diagnosis to their death is 107 days. However, in their competing risk value, which is my sense_CMP risk, is equal to 2 because they died, and that's my competing risk. Their sensor time or their follow-up time is 107 days. However, their status is 0 because they didn't experience my outcome of interest, which is SMN. So for the remainder of this presentation, I'm going to be focusing on my competing risk sensor variable. So now I want to dive into the cumulative incidence. And in competing risk, our cumulative incidence is called the cumulative incidence function. And just a refresher, the cumulative incidence is the probability that an event of interest occurs before a given time t. However, in competing risk analysis, the cumulative incidence function is the cumulative probability of failure from a specific cause over time, accounting for the fact that patients can fail from other causes, which are our competing risks. You might also recall that the cumulative incidence is equal to 1 minus the survival probability when only right censoring is present. So it's actually really simple to perform the cumulative incidence function in SAS when we do perform competing risk analysis. And I just want to highlight that this is done in SAS 9.4. So if you have a newer version of SAS, this can easily be done. And what this is done in is the proc life test. So I'm telling SAS, I want you to do a proc life test on my data. I want you to output the cumulative incidence function to a new data set that I'm calling CR_CIF_output. And I'm doing that just in case I want to look at the survival tables. And I want you to create a plot. And the plot I want you to create is the cumulative incidence function. And in brackets, I put test there. And what that test is I want you to test if there's any difference in the cumulative incidence functions between the different strata. Then I specify my time. So I want to do the time, my sensor time times my competing risk value variable, and then I'm going to censor observations with a value of 0. Now here's the crucial part, is I follow that by a slash and then event code equals 1. And what the event code equals 1 means is that I'm telling SAS that this is a competing risk analysis. And the value of 1 is my code of interest, which is time to SMN. Next, I'm going to specify my grouping variable, which is and then I do that by doing strata ITR. Because I want to know, is there any difference in the cumulative incidence functions between the different types of intensity of treatment received. If you do have an older version of SAS, this can also be done, but you have to run it in a macro. And this macro is built right into SAS. And I've put an example here. So you specify your data, the time variable, the status variable, which is your sensor and variable, the event of interest, so event equals 1, which is my SMN, the censored, and the grouping variable. So what SAS does is it gives me a cumulative incidence function plot. And I can see from this that the more intensive that the treatment received for the primary cancer is, the higher the cumulative incidence of a subsequent malignancy. SAS also gives me Gray's test for equality of the cumulative incidence functions. And I can see here that this is significant, or statistically significant, sorry. What this test doesn't tell me, though, is the relative nature between the cumulative incidence function. All it says is that somewhere between these four groups, there's a significant statistical difference between the strata. Now, what happens if we try to plot using the Kaplanmeier method? Well, the primary assumption in Kaplanmeier is that individuals who are censored have the same survival probability as those who are continued to be followed. However, this is actually violated in competing risk analysis. What it results in is that it biases our survival probability. And it's biased due to the fact that the probability of the event occurring is modified, or it's conditional, by the preceding competing event. So traditional Kaplan-Meier curves will result in the biased and overestimated results in the presence of competing risks. So here I'm just showing, for example, we've seen this before, proc life test. However, I'm using the status variable here, and I'm not telling SAS that this is competing risk analysis. And the output I get here is much different than the cumulative incidence function. You can see here that it's actually overestimating each of the cumulative incidence functions. And it also gives us, as well, the test of equality over a strata, which is the equivalent in Kaplan-Meier of the grade test in competing risk. What proc life test also does is it gives you this little summary table. So on the left-hand side, I have the Kaplan-Meier, and I have my failed observations, which are my SMN. However, using the cumulative incidence function on the right, I can also see the number of competing events that occur within my different strata of my ITR. So I can see that as you go down the intensity of treatment, the number of deaths actually does increase. So next I want to talk about quantifying the risk, and I'm going to first start with one method, the subdistributional hazard of competing risk analysis. So this method was proposed by Fine and Gray in 1999, and it's a method of using the proportional hazards model, and it aims at examining the effects of covariates in the context of competing risks. And what it does is it uses the cumulative incidence function, which I just presented, to model the subdistributional hazards. Now, what's really critical here is that the risk set is different, or it's not what we're used to. The risk set actually contains subjects who are currently event-free, as well as those who have previously experienced a competing event. And the subdistributional hazard subjects who are censored from the competing risk actually remain in the risk set and are given a weight that reduces with censoring time. So in the newer version of SAS 9.4, it's actually really easy to perform the Fine and Gray method of competing risk analysis. And that's contained within the proc pH reg statement. So in this little bit of code here, I specify the class statement. And the class statement tells SAS that I want you to treat these variables as categorical. So in the class statement, I first start off with my ITR, which is my main exposure of interest. And in the brackets, I set ref equal to least intensive. So I'm telling SAS, this is my reference group. I want you to compare the hazard ratios of the different levels of intensity of treatment to the least intensive. Then I'm also specifying in the class group my diagnosis group, as well as whether or not an individual or the patient, received radiation as part of their primary cancer treatment. Next in my model, I want to specify the model statement. So I'm telling SAS, this is the model I want you to run. So I want you to have my censored time or my follow-up time, and then the little star, and then my competing risks variable. And in the brackets, I have 0. And 0 is what notes a censored observation in my cohort. And then I'm going to specify the model. So in my model, I have ITR, which is my main outcome of interest, exposure of interest. I have the primary diagnosis age, diagnosis group, and whether or not they received radiation. And here's what really separates the pH reg for competing risk analysis is the event code. So I follow my model statement with a slash, and then I have RL, which is the risk limit, and that's what gives me my hazard ratios, and then I have event code. And once SAS sees event code, it knows I need to do competing risk analysis. And the event code is equal to 1 because that's the outcome of interest that I'm concerned with in this study, which is my SMN variable. If you're using an older version of SAS, unfortunately, you have to use a macro again. It will perform the same regression or the same modeling regression. And I put more in here of where you can find this macro, as well as a paper that does dive into it as well. So now into some of the output that we get. I can see that my I can see that my event of interest is 1, which is my SMN. The competing events, which are my deaths, are set to 2, and my censored variable are those who don't experience either the event or the competing risk, and those are set to equal to 0. Then I'm looking at my failure outcomes. So SAS tells me that my event of interest, I had 323 SMNs in my cohort. However, it also tells me the amount of competing events that I also had in my cohort, which are slightly over 2,100. So I know that there was 2,134 deaths within my cohort. Next, SAS gives me a type 3 test, which is a global null hypothesis test of the variables of interest. So I can see that my intensity of treatment is associated with SMN risk. However, the primary diagnosis age is not significant here, which to me kind of makes sense. Age shouldn't really be associated with the development of an SMN. Although I'm not a clinician, so I don't take that with a grain of salt. Next, I have my output with my hazard ratios, and this is what I'm really looking for. So since I specified in the class statement the ref equals 1, which is for my ITR, which is the least intensive, these hazard ratios are using that reference group. So I can see that as the more intensive the treatment received is, the higher the hazard ratio is. So it goes from 2 to 4.2 to almost 5. So there's a slight dose response in terms of the risk or the hazard ratio of SMN. Now the beauty of competing risk analysis is that we can actually quantify the hazard of the competing risk in our cohort when we run the analysis. And all we really need to do is change the event code of interest. It has the same interpretation as the previous output. So in this example here, I'm going to show what the hazard of death is in the presence of an SMN diagnosis as a competing risk, which is just the reciprocal of the previous slide. So here it's the exact same code as I previously shown. The only difference is now I've just specified event code equals to 2. So instead of SMN being the event of interest, I'm now telling SAS I want you to run a competing risk analysis, but my event of interest is 2, which are my deaths. Gives me the same amount of output. However, now we can see that my events of interest are now 2,134, which are my deaths, and my competing events are 323, which are my SMNs. Also, previously, age wasn't associated with the risk of SMN. However, when I do the competing risk analysis with death as my event of interest, I can now see that the primary diagnosis age is statistically significant or associated with the death hazard. Now, one thing I need to make clear here is that I've treated age as a continuous variable. If I were to categorize it into infants and older groups, it would be actually more statistically significant. So from this output, I can see actually a much larger dose response in terms of the hazard ratios. And it kind of makes sense for me. The more intensive that the treatment is, usually the sicker the individual is, and the more at risk of dying, or the hazard will be much higher for these individuals because they're typically sicker. Now I want to show when we try to perform competing risk analysis, what happens when we actually don't distinguish the event type. So here, this code is pretty much the same. However, you'll notice that there's actually, I haven't specified the event code. So what SAS will now do is run a typical Cox proportional regression model, treating both SMNs and death as the event of interest. So we see 2,457 as our events. And we see that also age and ITR are both statistically significant. However, pretty much I can tell you right now that it's mainly the death events which are what's driving these hazard ratios. But this answers a different question. I'm not concerned with clumping SMNs and deaths together. So that's something to consider when performing competing risk analysis, that we actually have to specify the event code. Otherwise, it will give us estimates that we are not answering here. So next I want to touch on the cost-specific hazard, which is an alternative method of performing competing risk analysis in SAS. So the cost-specific hazard is actually just a standard Cox regression model with the competing risks treated as censored observations. So it's the instantaneous risk from a specific event after censoring for the competing risk and conditional on survival up until time t or later. Now the difference between this and the cumulative incidence, or sorry, the subdistributional hazard, is that the risk set actually decreases with time after individuals are censored for the competing event. Now one thing to note is that cost-specific hazards actually don't allow us to examine the effect of covariates on the cumulative incidence function. And this is what actually led to Fine and Gray to develop their regressional model that I proposed previously. So to perform cost-specific hazard regression in SAS, it's actually also quite simple. The only thing that changes here is now we're specifying in our model statement in the competing risk censored variable, in the brackets it has 0 and also 2. And what this does is I'm telling SAS, I want you to censor individuals with the value of 0 and 2, with 2 being the competing risk. And we can see from the regressional model that the censoring values that SAS is treating as censored are both 0 and 2. The events are the same, so we still have our 323 SMNs, and now we can see that there's over 9,000 censored individuals. Again, we get the same values, well, not the same values, but close enough. The ITR is statistically significant, as well as age is not associated with our event here, which is our SMNs. However, there is a slight difference in our hazard ratios for the ITRs. So when we did the subdistributional hazard method, it was 2, 4, and then close to 5. But now we see it's 2.4, 5, and 9.3. And the result of this is because of the risk sets that's actually used when using the cost-specific hazard. Every time an individual experiences the competing risk, so here it would be death, they're eliminated from the risk set. And that's what's really driving this inflated hazard ratios, and that's something we need to consider when we decide which analyses to move forward with in our own survival analysis. Now, one little quirk here is, do we actually unintentionally model competing risk when we perform analyses? You can recall that I created a variable called status. And in status, 1 was equal to an SMN diagnosis, and 0 was equal to censored. And I also captured deaths in my censor variable, but they're contained within the value of 0. So just to test this, I'm running a Cox proportional regression again, same variables. The only thing that changes now is in my model statement. And in my model statement, instead of having the competing risk value, I've put this new status variable, which is the dichotomization. And I'm telling SAS to censor individuals with a value of 0. Now let's see what kind of happens, or what output do I get. Okay, this is the same. Interesting. These are the exact same values as I got previously when I ran a proportional Costspecific regression. And that's something that a lot of researchers don't actually consciously think of, is that we sometimes actually inherently perform competing risk analysis. We just might not realize it. And it's really all depends on how we define our sensor variables and our follow-up time. So the differences between the subdistribution and the cost-specific hazard are really mainly due to the risks that are used. When the competing risk is common, which is what I showed in my example here, the cost-specific hazards will overestimate the hazard. And that's due to, and the degree of overestimation depends on the frequency and the distribution of the competing events. So since deaths in my cohort were actually quite frequent, it caused that overestimation due to the risk set changing. So in summary, competing risk analysis is actually considered when a subject is at risk of more than one mutually exclusive outcome event. We can model separate survival probabilities for the outcome of interest in the presence of competing events. The analysis is actually pretty straightforward and easily performed in newer versions of SAS with slight modifications to both the proc life test and the proc pH reg procedures. And there are two different methods which are slightly different to perform competing risk analysis in SAS, both the subdistributional hazards method and the cost-specific hazards. I've put up a few additional readings in case anyone wants to dive deeper into this. These are actually really great resources, and I highly recommend to look at these if you are interested. Thank you.
Great. Well, thank you, Giancarlo. I guess at this point we'll open the floor for any questions for anyone who's on the call. Maybe I'll start with one question. So Giancarlo, I just tried to figure out when I would actually use the fine and gray method over the cause-specific. Is it really related to how frequently my competing risk outcome occurs?
Yes, that's one reason too, absolutely. The subdistributional hazard method, which is the fine and gray method, it actually allows you to easily predict the cumulative incidence function. However, since the cost-specific method or the model censors all individuals who do not experience the event of interest, prediction for the cumulative incidence function is actually not that easy to do, and it's actually quite difficult.
Okay, thank you. Any other questions? All right, well, at this point, I'd like to thank Giancarlo for coming and presenting to the Research Champion Group. And as previously, this presentation will, the recording of this presentation will be uploaded and available on the website for people to review at a later time. So thank you again, and watch your emails for subsequent presentations coming out as part of the Research Champion Group. Thank you.
Thank you.